Today, we will talk about why is the Sun important. The Sun is an ordinary star, one of about 100 billion in our galaxy, the Milky Way. The Sun has extremely important influences on our planet. It drives weather, ocean currents, seasons, and climate, and makes plant life possible through photosynthesis. Without the Sun's heat and light, life on Earth would not exist. About 4.5 billion years ago, the Sun began to take shape from a molecular cloud that was mainly composed of hydrogen and helium. A nearby supernova emitted a shockwave, which came in contact with the molecular cloud and energized it. The molecular cloud began to compress, and some regions of gas collapsed under their own gravitational pull. As one of these regions collapsed, it also began to rotate and heat up from increasing pressure. Much of the hydrogen and helium remained in the center of this hot, rotating mass. Eventually, the gases heated up enough to begin nuclear fusion and became the Sun in our solar system. Other parts of the molecular cloud cooled into a disk around the brand new Sun and became planets, asteroids, comets, and other bodies in our solar system. The Sun is about 150 million kilometers, 93 million miles, from Earth. This distance, called an astronomical unit, AU, is a standard measure of distance for astronomers and astrophysicists. An AU can be measured at light speed, or the time it takes for a photon of light to travel from the Sun to Earth. It takes light on the Sun about 8 minutes and 19 seconds to reach Earth. The radius of the Sun, or the distance from the very center to the outer limits, is about 700,000 kilometers, 432,000 miles. That distance is about 109 times the size of Earth's radius. The Sun not only has a much larger radius than Earth, it is also much more massive. The Sun's mass is more than 333,000 times that of Earth, and contains about 99.8% of all of the mass in the entire solar system. Composition. The Sun is made up of a blazing combination of gases. These gases are actually in the form of plasma. Plasma is a state of matter similar to gas, but with most of the particles ionized. This means the particles have an increased or reduced number of electrons. About 3/4 of the Sun is hydrogen, which is constantly fusing together and creating helium by a process called nuclear fusion. Helium makes up almost the entire remaining quarter. A very small percentage, 1.69%, of the Sun's mass is made up of other gases and metals: iron, nickel, oxygen, silicon, sulfur, magnesium, carbon, neon, calcium, and chromium. This 1.69% may seem insignificant, but its mass is still 5,628 times the mass of Earth. The Sun is not a solid mass. It does not have easily identifiable boundaries like rocky planets like Earth. Instead, the Sun is composed of layers made up almost entirely of hydrogen and helium. These gases carry out different functions in each layer, and the Sun's layers are measured by their percentage of the Sun's total radius. The Sun is permeated and somewhat controlled by a magnetic field. The magnetic field is defined by a combination of 3 complex mechanisms: a circular electric current that runs through the Sun, layers of the Sun that rotate at different speeds, and the Sun's ability to conduct electricity. Near the Sun's equator, magnetic field lines make small loops near the surface. Magnetic field lines that flow through the poles extend much farther, thousands of kilometers, before returning to the opposite pole. The Sun rotates around its own axis, just like Earth. The Sun rotates counterclockwise and takes between 25 and 35 days to complete a single rotation. The Sun orbits clockwise around the center of the Milky Way. Its orbit is between 24,000 and 26,000 light-years away from the galactic center. The Sun takes about 225 million to 250 million years to orbit one time around the galactic center. Electromagnetic radiation. The Sun's energy travels to Earth at the speed of light in the form of electromagnetic radiation, EMR. The electromagnetic spectrum exists as waves of different frequencies and wavelengths. The frequency of a wave represents how many times the wave repeats itself in a certain unit of time. Waves with very short wavelengths repeat themselves several times in a given unit of time, so they are high frequency. In contrast, Low-frequency waves have much longer wavelengths. The vast majority of electromagnetic waves that come from the sun are invisible to us. The most high-frequency waves emitted by the sun are gamma rays, X-rays, and ultraviolet radiation, UV rays. The most harmful UV rays are almost completely absorbed by Earth's atmosphere. Less potent UV rays travel through the atmosphere and can cause sunburn. The sun also emits infrared radiation, whose waves are a much lower frequency. Most heat from the sun arrives as infrared energy. Sandwiched between infrared and UV is the visible spectrum, which contains all the colors we, as humans, can see. The color red has the longest wavelengths, closest to infrared, and violet, closest to UV, the shortest. The sun itself is white, which means it contains all the colors in the visible spectrum. The sun appears orangish yellow because the blue light it emits has a shorter wavelength and is scattered in the atmosphere, the same process that makes the sky appear blue. Astronomers, however, call the sun a yellow dwarf star because its colors fall within the yellow-green section of the electromagnetic spectrum. Evolution of the sun. The sun, although it has sustained all life on our planet, will not shine forever. The sun has already existed for about 4.5 billion years. The process of nuclear fusion, which creates the heat and light that make life on our planet possible, is also the process that slowly changes the sun's composition. Through nuclear fusion, the sun is constantly using up the hydrogen in its core. Every second, the sun fuses around 620 million metric tons of hydrogen into helium. At this stage in the sun's life, its core is about 74% hydrogen. Over the next 5 billion years, the sun will burn through most of its hydrogen, and helium will become its major source of fuel. Over those 5 billion years, the sun will go from yellow dwarf to red giant. When almost all of the hydrogen in the sun's core has been consumed, the core will contract and heat up, increasing the amount of nuclear fusion that takes place. The outer layers of the sun will expand from this extra energy. The sun will expand to about 200 times its current radius, swallowing Mercury and Venus. Astrophysicists debate whether Earth's orbit would expand beyond the sun's reach, or if our planet would be engulfed by the sun as well. As the sun expands, it will spread its energy over a larger surface area, which has an overall cooling effect on the star. This cooling will shift the sun's visible light to a reddish color, a red giant. Eventually, the sun's core reaches a temperature of about 100 million on the Kelvin scale, almost 100 million degrees Celsius, or 180 million degrees Fahrenheit, the common scientific scale for measuring temperature. When it reaches this temperature, helium will begin fusing to create carbon, a much heavier element. This will cause intense solar wind and other solar activity, which will eventually throw off the entire outer layers of the sun. The red giant phase will be over. Only the sun's carbon core will be left, and as a white dwarf, it will not create or emit energy. What do you think of our video? Let me know in the comment section below. Before you go, please hit the like button and subscribe to my channel. Thanks for watching.